An interesting phenomena called priority inversion happens once we introduce priorities into the scheduling. Consider the following situation, and we'll use the shortest job first scheduling to illustrate what happens. We have 3 threads. The first one has the highest priority, and P3 is the lowest priority. So T1 is the highest priority thread, and T3 is the lowest one. For this example, we've left out the execution times. Just assume that they take some longer amount of time, all these tasks, and that the time graph continues into the future. Initially, T3 is the only task in the system, so T3 executes. And let's say that T3 also acquired a lock. Now, T2 arrives. T2 has higher priority than T3, so T3 will be preempted and T2 gets to execute. Now, time 5, T1 arrives. It has higher priority than T2, so T2 will be preempted. And then T1 executes for 2 time units, and at that point, it needs to acquire a lock, and this happens to be the exact same lock that's already held by T3. Unfortunately, that won't happen. T1 cannot acquire the lock, so T1 at that point is put on a wait queue associated with the lock. We schedule the next highest priority task that's runnable. That's going to be T2. And then T2 will execute as long as it needs. And let's say in this case, we locked out T2 really only needed to execute for 2 more units. At that point, T2 completes. We schedule the next highest priority runnable task. The only runnable task in the system is T3. So T3 will get to execute. And in fact, T3 will execute for as long as it needs to until it releases the lock. Only after T3 releases the lock will T1 become runnable. And then once T1 becomes runnable again, it is the highest priority thread. So T1 will preempt T3 and T1 will continue its execution. So it will acquire the lock and continue executing. So based on the priority in the system, we were expecting that T1 will complete before T2, and then T3, the lowest priority thread, will be the last one to complete. However, that's not what happened, and the actual order of execution was as follows. T2, the medium priority thread, followed by T3, the lowest priority thread, followed by finally T1, the highest priority task in the system. So the priorities of these tasks were inverted. This is what we call priority inversion. A solution to this problem would have been to temporarily boost the priority of the mutex owner. What that means is that at this particular point, when the highest priority thread needs to acquire a lock that's owned by a low priority thread, the priority of T3 is temporarily boosted to be basically at the same level as T1. Then T1 could not have proceeded just as before, given that the lock is owned by somebody else. However, instead of scheduling T2, we would have scheduled T3. Its priority would have been temporarily boosted to that of T1, so it would have been higher than T2. And then T2 would have completed, and so at least we would have been able to go ahead and start executing T1 at this particular point, and then we would not have had to wait for T2 to complete, for the medium priority thread to get in the middle. This technique of boosting the priority of the mutex owner, this is why, for instance, it is useful to keep track of who is the current owner of the mutex. This is why we said we want to have this kind of information in the mutex data structure. And obviously, if we're temporarily boosting the priority of the mutex owner, we should lower its priority once it releases the mutex. The only reason why we were boosting its priority was so as to be able to schedule the highest priority thread to run as soon as possible. So we wanted to make sure that the mutex is released as soon as possible. This is a common technique that's currently present in many operating systems.